Yes, I lived on French Hill, right? Or next to it. Do you know where it is? And it's called French Hill because it's full of French. הגבעה הצרפתית בדיוק. אתה מכיר את המקום? Okay, so let's get going with that. אבל אתה מכיר, נחמד. Okay, let's go on, guys. Let's sorry for the chatter, but I hope you don't mind it too much. I can be distracted by things. So first question again, guys. So appear, all of you, turn your cameras on if you can. I really like seeing your faces, whether they are confused or excited. Today is new. Nicole, yes, good. Nicole is here. I needed you because we might address your trouble from last class. Okay, so do you remember, before I talk about it, what are asymptotes, guys? Could anybody tell me what is an asymptote? What's the idea?
Is it when it goes across the x-axis, I think?
Well, you see, you say it goes, but first of all, it is very vague to me. What is it? So what do you visualize when you say, oh, there is an asymptote? What are you seeing?
When the line of the graph goes across the x-axis?
When you mean when the graph crosses the x-axis? No, it doesn't have to cross the x-axis.
Well, the y-axis, I mean.
No, it doesn't have to cross the y-axis. An asymptote is something, what? Getting close to a number, that's a sort of limit, guys, right? So look at it. When we take limit as x goes to infinity, that's where we kind of stopped, right? That means we take the function and we plug into the function very large values. Is that clear? We take the function and we feed it very large values and then try to predict what happens to this function. Now, if the function approaches a particular number, let's say if the limit approaches 5, then what is that 5 telling us about the graph of this function? That's when we speak of asymptotes. Tesla said it, a function, oh, okay, so somebody's quoting Tesla. Guys, come on. What is that 5 signifying? You forgot it? So an asymptote, again, you see the word, if you kind of think about it, if you use the word it or crosses, whatnot, you can possibly forget it. What an asymptote is a shape that is very familiar to you, to which you compare the graph. You're saying the graph is like that shape. And the simplest shape for curves are straight lines. And straight lines can be horizontal. Do you agree? So a horizontal asymptote is just another way of saying, I am looking at my graph and I see a horizontal line. Are you with me? That goes on or whatnot. So let me just quickly show you a graph, right? Let me show you one of the graphs. You don't have to know at the moment, it's trigonometry. You don't have to know how I figure it, but look at it, guys. You see this graph? Yes, you can all see this graph. It looks rather complicated, correct? But when I ask what is the asymptote, what happens if I plug x closer to infinity? The function cosine of 1 over x, guys, is just the altitude. So at this x, that's cosine of 1 over x. At this x, the altitude is 0. At this, it's below the x-axis, you see? And we're meandering. You see what's happening? This curve crosses the x-axis many times, but it doesn't matter if it crosses the x-axis or not. It's not at all what we care about. Do you see what happens, guys? I'm moving to the right. So imagine that you are in a train, and the train goes, and you're looking out of your window and you're looking at this curve. And then as you're about to fall asleep, what are you beginning to see? You are beginning to see that this curve starts to look like what? Tell me, what does it look like? Look at it. I go further and 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 further. And what does the curve look to you like? Horizontal line. Do you see that? And so, for instance, it's a very famous song and a very famous poem, if you know Russian, right? В дыме поезда поля. In the smoke of the train, I see planes and planes. So I imagine I'm departing from everything I cared about and loved, right? Leaving it all behind, and I go. And what I'm seeing suddenly is that there is a huge plane. And because we're in one dimension right now, that huge plane is a horizontal line. That's the asymptote. Do you understand? Is it clear, guys? So it has nothing to do with crossing anything or not crossing anything. It has to do with the fact that the graph that was complicated starts looking very simple and familiar. It looks like a horizontal line. Good? And because we are not always looking with our eyes, we are using mathematics. We are replacing our eyes with mathematics. And so that is supposed to tell me what I'm supposed to see on the outside, even if I don't see anything, even if my eyes are closed. Good. So for that, guys, tell me, please, how to calculate what happens here. What would it mean to calculate if it has a horizontal asymptote or not? What would you do? This function f of x then represents the altitude, right? For any x, that represents how to calculate the altitude on which you are standing. So it has a horizontal asymptote if you move far to the right or maybe far to the left, decide where you want to drive, and you should begin seeing a horizontal line. Good? So for that, it's useful to calculate limit as x goes to infinity. Again, guys, I think we did it last time, but calculate it fast and calculate it again, please. Okay, Abraham, exactly, the answer is 2. 2. You all see why it's 2, guys. The reason it's 2, here is a slow calculation of why it's 2, but you see, I factor the leading power x out, which is x cubed. Do you see how I factored, guys? I hope I don't need to re-explain it, right? It's I can distribute it. When I factor out each term, I just divide by x cubed, because that will be canceling the multiplication, right? When I factor something out, because you have the distributive law and it will multiply each term, I can just divide each of those terms, right? So it's x cubed. Here we have 2 plus x over x cubed minus 1 over x cubed. Same thing I do on the denominator. Clear? That has to be clear, guys, right? It's you're supposed to have taken precalculus and other things. Good. And so then here we have we have this limit, and this limit is very easy because 1 over x squared minus 1 over x cubed, each of those are going to 0 when x is large. Good. So the answer is 2. Now, what is that 2? That 2 is my altitude. So that means that my graph is y equals to 2. You understand why y equals to 2? Because instead of actually calculating through that function, calculating the altitude, I see that it's essentially the same as putting the number 2 for the altitude, right? For large values of x, the altitude is essentially 2. Now, if I were to move to the left, will I see the same horizontal asymptote? If I move in the left direction forever, will I see the same curve or something different? So that means that if I move to the left, I move towards minus infinity, correct? If I move towards minus infinity, will I see the same asymptote or I see something else? Well, let's look at it. Everything is working the same way. I can cancel out the x cube. I have numerator, denominator. Everything cancels out. Doesn't matter plus or minus infinity. Those will be positive or negative, but they are approaching 0. So it will be 2. So if I move forever to the left or forever to the right, I will see that the graph starts looking like a horizontal line. The same horizontal line. Do you understand, guys? So even from the last lecture, guys, you have to think very intuitively. You see, what is an asymptote? Very simply, it's like an analogy. Nothing more, right? It's like you're looking at a cloud and says it looks like a fluffy sheep. And when I say the cloud I'm looking at looks like a fluffy sheep, you can imagine it. And that's the point. When I give a comparison to something that I know. So that's to me what an asymptote is. It's just a comparison to something simple that I know and that you know. Good? It's very easy, guys. Yes, go ahead.
So I'm noticing that the bottom section where it's 2 plus 1 over x squared blah 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 over
Okay.
1 plus blah, blah, the bottom one it's 1 plus 1 over x plus 5 over x3. So when it's limit and the x is it's for infinity, do you just like you cancel anything
No,
with
you don't
x.
cancel. You see,
because it's
here is what you
separate.
think about. Look what happens. What is x? There is no x. I'm just plugging. That means a very large number. What this means is instead of whether you see this expression, you see a huge number. So 1 over a huge number is barely visible. It's 0. It's essentially 0. It's not really 0, but it's very close to 0. Do you see? So those terms, they are vanishing because if I plug in tremendously large number, 1 divided by a tremendously large number is not visible. It's like 0. So that's what when I say that the answer is 2. You see, guys?
So in the case where the limit x goes to infinity, those things with the x just vanish and all the constants are left there.
Yes, they vanish. But again, guys, you see, I want to admonish you against trying to pick up rules. That's not, you see, if you're going to try to make it like if then, it's going to be a very difficult course, right? But if you understand why something happens, then it's natural. You don't need to have any rules. You see, 1 over a large number is not visible. So that's why it vanishes. So there's nothing that I'm doing here that's not like I'm saying you're allowed to do this or not allowed to do this. There's no such thing as allowed in mathematics. You can do anything you like as long as it doesn't violate the laws of nature, right? Because then that's all. Good. So the answer here is 2. I hope you understand it. And the answer when you push limit as x goes to minus infinity is 2. And here I mention again, 1 over x. The limit, if I select x going to infinity or minus infinity, will be 0. So that means y equals 0 is a horizontal asymptote. You understand? That means that the graph looks like the x-axis when I move far enough to the right or far enough to the left. Okay, guys. Now, there is nothing special about such asymptotes, right? I can compare to other shapes. Maybe I know that a parabola is familiar. So y equals x squared is a familiar shape, or y equals x cubed might be a familiar shape. And if that's the case, I can call it parabolic asymptotes. Or if I have a line, look at it, guys. If I have a sort of line, in my asymptote can be mx plus b. Mx plus b is just a line that is not horizontal, but it's a familiar shape. You understand? And I will call that familiar shape an asymptote. Everyone's clear? Has nothing to do with intersecting something or not intersecting something. Has everything to do with the shape of the graph is now compared to something very simple. Clear? Wonderful. So if it's clear, help me see if you can do that yourself. Tell me, what do you think is the limit as x goes to infinity of this expression? And do we have any asymptotes? Right? Do we have a horizontal asymptote, for instance, or do we have something else? Okay, Abraham is saying no asymptote. Do you agree? No asymptote in my language, by the way, guys. No horizontal asymptote, maybe you mean, right? No asymptote is like it's not similar to anything. That's how I understand when you say no asymptote. Okay, it's not similar to anything. Let's just look at it. Okay, let's do it together, guys. So first of all, you see that if I factor the leading power x, it's x to the 6 times 1 plus 1 over x to the 6. Here I factor x to the 4. And you can see that what it simplifies to is x squared, I say plus or minus here, times this expression. Now, what x squared is multiplied by goes to 1, and then we have infinity times 1 is infinity. In other words, number is getting larger times a number similar to 1. We are seeing a huge number, right? But that doesn't mean there is no asymptote. No asymptote is almost meaningless in my mind, right? No asymptote means it's not similar to anything simpler. Right? No horizontal asymptote, that's correct. Right? It's not horizontal because the quantity going to infinity means that as I move to the right, the graph is growing up. You understand? But it doesn't mean it's not similar to anything. Let's do long division, guys. I hope you understand or remember long division. It's supposed to be something you learned from before. Well, let's see if it's a diagonal line. What is this thing? Okay, guys? So I do long division. Are you ready? So I am going to divide x to the 6 plus 1 by x to the 4 plus 1. And what I need to get to x to the 6, I need to multiply x to the 4 by x squared. So I put the x squared here. Then you multiply x squared through this expression, and you have x to the 6 plus x squared. In the next problem, maybe I will do it side by side in case you forgot one time, okay? But you need to know long division, guys. Do you see this? I now subtract, and what I'm left with is minus x squared plus 1. You see, this minus x squared plus 1. So that means that x to the 6 plus 1 over x to the 4 plus 1 equals to x squared plus this vestigial part. That vestigial part is called perturbation. In other words, it's some sort of disturbance of the x squared. You see that if I take just that part, are you seeing this? This part will go to 0. Do you agree? Limit as x goes to infinity of that part will go to 0. Clear? Because the leading power is x to the 4, factor it out, and here the leading power is x squared, it will be crushed to 0, which means if I plug very large numbers to the right or very large numbers to the left, this part is essentially not important. It's calculating a number very close to 0. Yes? So that limit is close to 0, or it's going to 0. So that means that the asymptote that you have here is x squared. Y equals x squared. It's a quadratic asymptote. It means that this graph, if you look to the right, you eventually cannot distinguish it from the graph of y equals x squared. Do you understand how I reason it? Without visualizing anything, but just purely by mathematics, I see that it's x squared plus something, and you see that this something is very small, guys. If x is large, this something is almost invisible. So it's essentially x squared. Clear? So I would say that it has a quadratic asymptote y equals x squared because it's similar to that simpler shape. Good? Now, here we go, guys, and try to help me now. Let's see if you can do it. Next problem. We have x to the 5 plus x to the 4 minus 4x cubed plus 1. Good? Over x to the 4 minus 4x cubed plus 1. Help me figure out if there are asymptotes and what sort of asymptotes we have there. Okay, so no horizontal asymptote maybe, but maybe you can tell me what will be the shape of this graph. Even if it's not horizontal, I mean, maybe it's similar to something else. Yes, guys? Okay, John, interesting, but be careful. Maybe it's not just y equals x, maybe it's something similar, but not quite. I'll wait one more minute and we'll do it together. By the way, don't forget, I need to show you my commercial of what happens when some of you don't show to class. I know that not everybody comes. All right, let's be doing it together, guys. I will do it side by side in case you don't remember how to do long division. You see, so what you do is, look at it. I'll do several steps. You write the division side. Here you write the thing that needs to be divided, right? The things that needs to be divided is x to the power of 5 plus x to the power of 4 minus 4x cubed plus 1. Okay, now I don't want to write it here. I will just underline. This is the divider or divisor is written here. Good. And then you begin asking yourself, okay, look at this number. It's x to the 4. What must I multiply the leading term to get x to the 5? Clearly, I need to multiply by x. Do you agree? So I put the x here. And then once I put the x here, I multiply it by this expression. Do you see? X times x to the 4 is x to the 5. X times minus 4x cubed, it's minus 4x to the 4. Yes? And then x times 1, it's plus x. And I subtract. You see what I do? I subtract. Now, once I subtract, what happens? The x to the 5, look at it, the minus just distributes. So I am left with x to the 4 minus 4x to the 4. So it means 5x to the 4. Are you seeing what I'm doing, guys? I mean, I'm explaining arithmetic. Minus distributes here, here, and here, and then you add them.
Professor,
Yes.
how did you get x5? No, how'd you get? What's the first thing you did again? Where you got the x on top,
You
then
see
the
x to the
minus
5? I need to figure out how to get x to the 5. So here I have x to the 4. What do I multiply x to the 4 by to get x to the 5? I need to
You
multiply it by
multiplied it by x, but why did you do it by x?
it's a division algorithm. I mean, I'm trying to see how to produce x to the. So basically, what is division? Division means that there is a multiplication. Let me just quickly show you. You see, guys, what is division? If you say, for example, one second, somebody is asking something. Yes, Grant. Grant is in the notes saying x times x to the 4 is x to the 5. You add exponents. Okay. You have to ask yourself, what is it that you do with division? With division, if you're saying, let's say, take p and divide by q, what you are saying that if the answer is r, then that means that p is equal to r multiplied by q, and I'm trying to guess what is that r. You understand? So, for instance, if we have here, if we are dividing. Look at it. If we're dividing on the top, it was what? It was x to the 5 plus x to the 4 minus 4x cubed plus 1. And on the bottom, I have x to the 4. What was that next? I forget. What was that? X to the 4 minus 4x cubed minus 4x cubed, and what did I say, plus, where is it? Plus 1, right? Thank you. Plus 1, right? What am I really figuring out when I calculate this quotient? I am saying x to the 5 plus x to the 4 minus 4x cubed plus 1 is equal to something, right? Something which would be ax to some power n plus like an minus 1 x to the power of n minus 1 onwards times times x to the 4 onwards. You understand? So then I want to know this times that must give me x to the 5, biggest power. And that's why I'm reasoning what long division is doing is just precisely this. Precisely this. If guys, you want assistance with this thing, you know, I mean, you see, this is what I mean, guys. You are supposed to know all of those things before this class. If you do not, you come to my office hours, you don't leave. Failure rate in this class, you know, objectively is 50%, if not more. In my class, of course, I spare people. Sometimes not because I think that they should be spared. I feel bad for them, but you understand. I mean, you are supposed to work very hard for this class to catch up to what you do not know. So, yeah, so again, when I try to accomplish here is this x, when I multiply it by x to the 4, this is basically this multiplied by this is supposed to give me this, you understand? So I'm trying to guess what's on the numerator. So clearly the first term has to be x, right? So I multiply it by x and you have x to the 5, blah, blah. Basically you have x to the 5 minus 4x to the 4 plus x. Why do I subtract? Because I already packaged it, right? So I subtract and I get, let me just maybe we'll take this deviation. Maybe that will help. I don't know. Let's. What do you do when you let's say, for instance, when you take, let's say, when you say, let's say 15 divided by 7, right? How do you simplify that? So what is that you're trying to get? You're trying to see how many times that can I get maximum amount of 7 until I get to 15, right? So what you do is you think, okay, I can write 15 as what? At 2 times 7, right? Plus 1. Do you agree? 2 times 7 plus 1.
Yes.
One second, give me a moment, guys. I'm trying to think. My circuits are a little in explaining it. I think I'm just thinking too much how confused you are. I cannot figure out what I should say for a moment. Okay, so stay. If you're confused about this thing, I was not prepared to teach you arithmetic right now, right? So if you're confused about this thing, you stay after class and we discuss it. Okay, all of you. Division algorithm, precisely, right? So stay after class, we will try to understand the division algorithm in case you don't think about it, and think about it deeper, right? Why does it work? Yeah, sorry guys, I'm a bit, so when you carry this calculation, what you get is x plus 5. Just carry this calculation, you will get x plus 5. I want to move on through this lecture. After class, we will go through this long division. We will calculate it very slowly. Just stay after class, okay? So that means that my my oblique asymptote is x plus 5. Let's see how the graph looks like. Look at it. If I move to the right, do you see what's happening? I move to the right. Do you see that what I'm seeing is an oblique line? Yes? So now let's think about how to carry those limits. Let's think about how to carry those limits very fast. Think, so I call it simply think in the box. Okay, so if you have a rational function, let's make this calculation once. Let's make this calculation once. And so what we have is, this is an example of a rational function, okay? I'm going to try to explain why you only need to pay attention to the leading powers of both numerator and denominator. Good. So you see that in those leading powers, I will get this. This is my limit, and what this limit is will determine what the function equals to. So here is what happens, guys. I can factor from the numerator the leading power of x, which is x to the n, and the leading power of x on the bottom. And why I do that is because when I factor it out, all remaining terms are divided by at least x. Do you see that? There is a division by at least x. And so what happens if you push limit as x goes to infinity? What happens is that in this parenthesis, everything becomes 0 except for the leading term of a and the leading term of b. And here we have this ratio xn over xm. And so that's going to be the ratio I need to consider for the limit. Do you follow me, guys? Are you with me still, guys, or you're very confused today? My circuits were, for a moment, how do you say, fried, right? There is in the explanation, not in what I see, but in the ability to explain a certain small thing, you know, there was a sort of break in my mind. It's damaged now. Good?
Can you repeat it again?
Yes. Do you see this line, guys? Do you understand why think inside of the box method works? Why I need to pay attention only to the top and bottom boxes and not to anything else? Yes? So why can I ignore everything else here? Look at it. If I factor x to, why do I factor the biggest power? If I factor the biggest power, do you look at it? Everything except for the first terms is divided by at least x, which means that if x goes to infinity, those terms are squashed and disappearing to 0, which means they are not important. Do you understand? That's what I'm trying to say, guys. Think about it. By the way, don't you all leave? You see, I just didn't want to hold the class. I was thinking about how much I have to go today, how much farther. You stay after class and we will do long division if that's what you don't know. Okay, we'll go slower. I just needed, I need a few moments to calibrate myself to be able to explain it to you. But you need to know it. So here, guys, is a test. You see A, B, and C. I want you to tell me the solution A equal to, B equal to, C equal to, and tell me where you have horizontal asymptotes. Okay, so first I want you to tell me the limits. A, B, and C as x goes to infinity or minus infinity, and give me the simultaneous solution for all three when you're answering. So you say A equal to, B equal to, C equal to. Understood? Okay, wonderful. Okay, guys, if you could, so that it's easy for me to remember all of your answers neatly, just write all three together before you write one. Just solve all of them and write them together in my text so that I can see it. Okay, for C, so look at C again. Alexandra, look at C, check yourself. B and C, right? So, okay. Ready? It should be very quick, guys. So here is what the results are. I just look at the leading power of both numerator and denominator. And the answer here is clearly 1/2. What is that 1/2? That means I have a horizontal asymptote, y equals to 1/2. Do you agree? It means that if I push to infinity or minus infinity, this fraction collapses to 1/2. Everybody says that? You understand why I ignored everything else, every other term except for the power 10 here. In B, it's the same, the limit is the same as 6x cubed over 3x squared, which will be plus minus infinity. This B will be, if you look to the left or right, it would look like a straight line. It would have an oblique asymptote. You understand? If you scroll to the right or scroll to the left, it would look like an incline. Is that clear, guys? And here the answer is 0.
Quick question.
Go ahead.
So A is 1/2, whereas B, because it's not a fraction, it could be infinity, right?
Because of, no, it's because look at it. Here we have, when you simplify it, it's like, it's 2x. This becomes, the limit is the same as that of 2x. It's like 2 times a large number. Okay, so that makes it infinity.
But I mean, the same doesn't apply for 1/2.
But x
Because
to the
it
10
cannot
divided by
be.
x to the 10 is 1. So 5x to the 10 divided by 10x to the 10 is 5 over 10, which is that's how it's 1/2. It disappears. But here it's third power over second power. The x does not disappear. It's 2x that remains. Yes?
Say that again about
2x remains here. That's what happens here. It's 2x. Here we have 6x cubed over 3x squared. What remains is 2x. Look at it. X cubed over x squared is x.
Oh yeah, I forgot that.
Good.
You subtract the exponent. I forgot all about that.
Yes, you say, well, subtracting, you just cancel it out, guys. You see, guys, here is what happens. If you're going to think about what do you do, exponents, you subtract or multiply. That means you need to see what's happening, right? If you just try to remember rules, there are going to be way too many, and you're not going to be finding your way around. You have to have intuition, right? You can, even when you program a robot will not be able to walk. Have you seen those robots that walk on the landscape? This, what do you call them, Atlas and all those things, right? From Boston Dynamics. You don't program this thing to say if the stone is this high, then that's how high you lift your leg. It has to be a sort of heuristic. You have to feel your way. It's similar in mathematics. You have to feel your way. So here is the explanation for what is vertical asymptote, guys. A vertical asymptote is if at some number, let's say the number a, as I push x to that number from left to right, I get plus or minus infinity. That creates a vertical asymptote. Why is it vertical asymptote? Look at it. In this case, x approaches close to a from the right, and here the graph climbs. The graph climbs. It has nowhere to go. It climbs along this dashed line. So it starts looking like a vertical asymptote. Are you with me? Good. Let me show you what this. Let's see if you can calculate yourself, guys. Here is an example. Root of 2x squared plus 1 over 3x minus 5. Could you please tell me what is the limit as I go to infinity or minus infinity? Tell me what it looks like. First, calculate limit as x goes to infinity. Let me know when you're ready. Okay, to infinity is, well, careful. It's not 1/2, John. Something, maybe somewhere there is a mistake. It's not 1/2. After class, we stay and solve many of those problems, right, guys? Because you're supposed to solve them fast. Yes, Aaron, √2/3. Sophia, very good. So, okay, guys, let's do it together. The limits, first of all, I observe that if I take limit as x goes to 5/3, then the answer will be plus or minus infinity. You see, why do I observe that? Numerator can digest any numbers. Do you agree? I mean, numerator, it's 2x² + 1. So underneath the root, the number is always positive. Clear? I take the input, square it, multiply it by 2 and add 1. The input underneath the root is always positive, and roots of positive numbers are defined. Denominator is a polynomial, so denominator is also defined for all numbers, but I am not allowed to divide by 0. There's this division operation, right? So when the denominator equals 0, I have some problems. So when does that happen? Clearly, when x equals to 5/3. Do you see that? Just solve the equation 3x - 5 = 0, and you get 5/3. You understand, guys? Yes? And then what? And then we push to the limit. If the numerator is some positive number, if I plug in here a number slightly more than 5/3, this will be like a 0+, which will make the quantity explode. I divided a finite positive number by something that is approaching 0 from the right. So with a plus here, it gets plus infinity. With a minus, you get minus infinity, because on the bottom you have 0 minus, and numerator is positive. You with me? Yes, guys?
Yes.
Wonderful. So now let's talk about limit as x goes to infinity. Look at it. I see 2x² + 1, so I will factor out x² inside of the root. So it's x² times 2 + 1/x². You agree? By distributive law, it's 2x² + 1 if I multiply it through. So when I factor out, all I do is each term, if I factor out x squared, each term I divide by x squared here. And on the denominator, I factor out an x. So it's x times 3 minus 5 over x. Now, root of a product is the product of roots. So I can move it like this. And now here is a mistake that people tend to make. They say root of x squared. They just say it's equal to x. But actually, it's equal to the absolute value of x. Let me emphasize that mistake is very common. So what does it mean, guys? When I say root of x squared, which means, it means this. There is no x. It means if you take a number and you multiply the number by itself, and then you take the root, what do you get? You sure? You see what I'm saying? What do you get? So let's try with, let's say, with positive numbers, right? So let's say if I take 3 squared, 3 I squared, and I take the square root, that's the square root of 9, which is 3. So that seems to suggest that if I take roots of positive numbers, if x is bigger than 0, then root of x squared equals to x. But what happens if x is less than 0? Let's see. We have root of minus 3 squared. What is that? That is root of 9, which is 3, which is absolute value of minus 3. You understand? So I observe that in general, root of x squared is not equal to x, but to be safe, it's equal to the absolute value of x. Is that clear? Good. Now, absolute value, well, so let's see what happens first with that particular problem, and then we'll get back to it, okay? So here is the absolute value of x, but x approaches infinity. So that means x itself is positive, and I can drop the absolute value. I can just say x. Yes? The absolute value is not necessary, it's just x. And so I have x times the root of 2 plus 1 over x squared, and here we have the x, we can cross it out, and now the limit is obvious. Look at it. It's underneath the root, it's 2 plus a small number. That's a perturbation. So when x is large, it's invisible, so it becomes root of 2, and on the denominator, we get 3. Yes? So it's root 2 over 3. You with me? So let's look at the graph. Here is the graph of it. Look at it, guys. Look at it. This is the graph near 0. And here is my conclusion. I move to the right, and I begin to see a straight line. Yes? Now, could you tell me what would happen? That's your question. What would happen if I move to the left? If I were to move to the left, what would be my answer? We only move to the right. So we see we have a horizontal asymptote on the right, which is y equal to root 2 over 3. What happens if I move to the left? Okay, so careful. Vertical asymptote, it will be at 5 over 3, Alexander, right? So there is a vertical asymptote at 5 over 3. That's why, because at 5 over 3, the graph has to explode up. So it looks like a straight line. I'll show you that asymptote. So the function becomes negative. Now, do you see why the function becomes negative, guys? Here is that calculation again. Now I take limit as x goes to minus infinity. And again, I do the same thing. Now I have root of x squared. And here is the step that confuses a lot of people. Look at it. I get that root of x squared is absolute value of x. Not x, but absolute value of x. Do you understand that? You understand what I mean, right? There is no such thing as x, just like there is no such thing as a person. Right? When I say a person, I mean you, and you, right? It's my way of speaking about everyone that is grouped somewhere, right? So what this is saying is this: if I take a number and I square it, and then I take the square root of it, what do I get? Do I get back the number, or maybe I do not get back the number? So what I'm saying, you get the size of the number, the absolute value of the number. Clear? And since x goes to minus infinity, look guys, since x goes to minus infinity, what I will get is minus x. You see that? You might ask, but isn't minus x negative? Is minus x positive or negative in the comments? Please tell me. Minus x. X going to minus infinity. Minus x. Is it a positive quantity or a negative quantity? Okay, so some people say negative. Minus x is negative. X stands for a number, right? Minus x. You cannot tell whether it's positive or negative. So it's negative times negative makes it positive. X is negative, right? What is x? X is a negative number. So minus x is a positive number. Do you follow? Depends on what the number is. And in this case, the number is negative. Here, do you see it in this example? Look at it, guys. What is absolute value of minus 3? The absolute value of minus 3 is the same as minus 3. Do you see? That's my x. And this negative makes it positive. Makes the full quantity positive. Do you understand that x, you see, you think very simply. You think here is a negative in front of something, you think it's negative. No, this stands for a number. If the number is negative, you multiply by another negative, you make it positive. Is that clear? Very. I mean, it's so clear that you will not make mistakes, because if you do, you know how I have also limit. You know, we're learning limits. There is a limit to my patience, right? Don't, I mean, I'm very patient, but don't overreach it. Well, my fuse is very long. It's not, but the explosion is very, very severe, right? The fuse is tremendously long, but the explosion, right? So don't make me reach that point. By the way, since we're talking about explosions, it's a good time to show you what happens if you decide to not show up to my class. I can show you 2 videos, right? Watch carefully.
I said the video isn't up.
Okay, apologies. 1 second. I see. Ready? M minus n times theta equal to a minus b, and that implies that theta is equal to a minus b divided on I minus 1 over kn minus n, where m and n are, again by assumption, not the same integer. And that would imply that theta is a rational number, which is a contradiction. We are saying by hypothesis that it is a rational number. So then, this implies, understood? This is mathematics. That's what it is, if you forgot. Good? Back to the limit. Who watched this? I have long videos that were watched longer. right? What I do is I tie you to this thing, and you will watch this video until you know mathematics, right? Until that's the only thing you know. Good. Here is that explanation again. Do you see that? So x stands for -3, so we take absolute value, and absolute value necessitates multiplying by minus to make it a positive number. Good. Now, guys, let's see how well you understand this thing. Calculate limit as x goes to infinity of root of x squared plus 1 minus x. See if you can do that. And then well, let's calculate first as x goes to infinity. See how far we get. Okay. One person has it. What about the rest of you? Okay, we have a few people. Good. All right, let's do it together, guys. So first of all, a lot of people begin thinking this way. So they see, okay, infinity squared plus 1 is infinity minus infinity. Well, that's infinity minus infinity, it's 0. Do you agree with that reasoning?
Can you go down a little bit more?
Yeah.
Because the pictures happen.
Good. So here is the question, right? So I square infinity plus 1, take the square root. What do I get? I get infinity. Minus infinity, I get 0. Do you agree with that reasoning? Is this good reasoning? Infinity minus infinity is 0.
I feel that this is a little weird because a little bit before you didn't say that infinity was a specific number. You just said it was a broad, like there was no limit. So it can be any number in the range. So
Precisely.
I
So we call it infinity. Thank you, Janie. That's exactly right. It's not a number. What is the symbol truly symbolizes in calculus? It just means a large number, very large number minus a very large number. But how large are they compared to each other? It's not specified. You understand? It's just one number grows, the other number grows, but we don't know the rate at which they grow. So it's not a number minus itself. It's just a crude symbol to say that something grows. It's not good enough to indicate what to do with it. So here is another strategy that we can do, guys. So you see, we have this conjugation or multiplying by the conjugate. So if we have something minus something and there is a root, I multiply by that something plus something. You see? If it's a minus b, I multiply by a plus b. And because I cannot change the expression, I divide by the same result. Good? And what happens in the numerator? It's just a squared minus b squared. Now a squared is just x squared plus 1, and b squared is x squared. So when I take the limit, so then I can cancel out the x squares, and I get 1 in the numerator. And then on the denominator, I have root of x squared plus 1 plus x. Now look what happens. It's 1 divided by something that grows large, which makes it 0. Do you understand? So the answer is correctly 0 in this case, but I cannot say infinity minus infinity. But in this form, it's 1 divided by a large number, because large number plus large number is large. On the other hand, guys, look at this reasoning here. Now, if x becomes negative, I can kind of say minus infinity squared plus 1 minus minus infinity, which is infinity plus infinity, and this is infinity. This reasoning is fine because there is no contradiction here, right? This number grows without bound, and this number grows without bound, so together they grow without bound, right? So the answer is infinity. Clear? The answer is growth without bound, to be precise. So in this case, this line is very simple. Guys, go ahead, see if you can do this. You see, I don't want to show too much of it. I hope you can see this equation. Root of 4x squared minus 3x minus 2x. I want you to calculate limit as x goes to infinity. And if you want to, I can tell you the answer in advance without doing any calculations. Let me know if you do. Okay, good. The answer, Erin, correct. Minus 3 over 4. Okay, so how do you do that, guys? Idea is very similar, at least for now. What you do is you multiply by the conjugate, you see, because it's of the form infinity minus infinity, so it's not clear. You multiply by the conjugate, and you see what the conjugate is, just the same expression, but with a plus. And why you do that is because then you can get rid of the square root. So it will be this number squared minus this number squared, which is, once you cancel it out, yes, and then I factored out x in the denominator at infinity, right? But pretty much it's really minus 3x over this expression. And in this expression, I can see what is the leading term there, right? The leading terms are, so there's a -3. The leading term here is here and here. So that would be a root of, on the bottom, root of 4x squared plus 2x, which is essentially 2x in this case plus 2x, because x approaches infinity, right? So it's going to be 2x plus 2x. Good? Okay, guys, so I'm clearing it. If you have questions regarding this, obviously do not go, right? You know how you have to study hours and hours after this class. You can spend some of those hours with me. So you can spend the next, after, when we're done with in office hours, we can do it at your pace.
Professor,
Yes.
is it safe to say that anytime we have a root of it, we would do the conjugate to help us get the
Well, I
solution?
mean, you see, you are trying to find some sort of regular thing to do all the time, but you should think very holistically. You look at the situation and figure out what's best. Okay, so we're very, very low right now. We barely covered anything, and we barely have any sort of view. But what you want to do is fly up high and see what is it that you're dealing with. If you can answer, very often you have better things to do. So, for instance, let me actually show you regarding your question. Let's say I'm going to give you this question. You can try doing it if you want. I'll give you 5 minutes, and I'll show you how fast I will do it. Okay, so here we go. Okay, guys, here is this calculation. Okay, the cube root of 8x cubed minus 5x squared minus 2x. Don't worry, don't feel anxious if you cannot solve it. I'm not claiming it's necessarily simple for you at the moment, but try, and I will show you I will solve it without doing anything. I would right away know the answer.
I have a quick question.
Go ahead.
To the right, when you said x, negative 3x over x, and then in parentheses radical, or I mean the root 4 minus blah blah blah. Why isn't there a 4x? Why is it just 4?
You mean here?
No, the previous one above. No, down.
Where are we looking?
Yeah, in that place. Because here. There was a 4. There was a 4x squared, and then you factor out x.
Let's see this line. Clear this up to this line.
The next one to the right. Yeah.
Okay. So the x, now it's a product. You see what I do? I factor it out. Look at it. I factor the x in here, and I factor it from the root. I actually skipped a bunch of steps. So what I have is I factor inside of the root, I factor out x squared. So it's like x squared multiplied by 4 minus 3 over x. And then when I factor the x squared out of the root, because x is positive, I know that root of x squared is just x in this case, just because x is positive. So I know that root of x squared is x. So then I have the x factor here. It's simply, look at it. From this line, from the denominator, what I do is root x squared 4 minus 3 over x, yes? Plus 2x. Here doesn't matter what it is. Then I factor out the x squared, so that becomes 1 over root, here I have x, and here I have 4 minus 3 over x, plus 2x. And finally, I factor out the x completely to cancel it out from the numerator. Make sense?
So you separated the x squared from the 4.
Yes.
Okay. You put in a separate parentheses under the root.
So yeah, so here you see I separate it from the 4 and from everything else. I want to factor it outside because you have root of a times b plus c is simply root of a times root of b plus c. Because it's a product. It doesn't matter what this is written, it's like product of two numbers. Root of a product of two numbers is the product of the roots. Good? All right, anybody has any success with this problem? Okay, time is up. And the answer is immediately minus 5 over 12. Now, how do I know that? I will teach you later. You don't have enough background yet, right? But the reason I know that is I think, what is this question really about? Okay, what is asked? So, for instance, in combinatorics, I like this example. So let's say 1 plus 2 plus 3 plus 100, right? Well, I look at it and right away say the answer is 101 times 100 divided by 2. And why do I know that's the immediate answer? It's because I imagine people are whispering, shh, I cannot tell how old is this guy, and he has a younger brother. He might be 2 years old, or he might be 101, right? And he has a younger brother. And then because I understand that this is just a code for something, I right away know what the solution. And that's one of the exciting things about mathematics, is that if you understand what something is speaking about, you know the meaning, you can quickly figure it out. And even more interestingly is that one sentence can have many, many meanings. All right, guys, so time for a little paradox. I hope you enjoy it. So let me tell you one of the most famous ancient paradoxes. It's called Xenos Paradox, and it's about motion. So Zeno believed that motion is impossible, or at least I'm not sure if he believed that. He had an interesting argument about it. Good. And and basically in the argument is, for instance, let's say you are trying to leave the room. And so to get to the door, you have to cross half the distance. Yes? But to cross half the distance, you have to move half of that half, which is a 1/4 distance. And to move that 1/4, you have to move 1/8 of a distance. But to do that, you need to move 1/16 of the distance, and so on and so forth. You have to move half of the half. And so what happens here is that before you reach the door, you have to take infinitely many steps. Now, before I continue, guys, you might think what's very weird what I'm saying here. Let's just see for a moment. Did you understand this paradox, and how many of you agree with Zeno or don't agree with Zeno? Can you truly get out of the room? Is this paradox silly? Can you stand up, open the door, and leave? Okay, Elazar, that's interesting. Maybe you can, maybe you can't. Elazar has just why does it matter if in one step I can cross it, or how the division is taking place? Again, if the room is small enough, I think you miss my point. You're missing Zeno's point, and I'm not sure I'll finish this full point. Yes, it's similar with a lot of things, similar to the fly, similar to many ideas, and it's not at all trivial once you think about it deeply. Okay, once you think about it deeply, there are many, many very surprising results, and I will try to. I'm not sure I'll get there today, but I will try to see if you believe this, at least in some way of phrasing it. All of you, I imagine, you stand up, you open doors, you walk around. So that's because of your experience, you have that feeling that you can do that. In fact, Pushkin wrote about it, right? He said, "Движения нет, сказал мудрец бородатый," and then the other guy just stood and left. He said, "Motion is impossible," said a bearded wise man, and the other just stood up and left. And I actually had that type of thing happen to me in high school. There was this class, and I was reading Kant, and space and time are intuition a priori. They don't exist. And the one girl, commonsensical girl, she got so annoyed with what I said, she just stood up and left. Right? So it's a sort of, is it a sort of thing like that? Or is it a sort of thing that when you think too much, you're completely confused? Or is it that there is something true about it? So first of all, do you understand what Zeno tried to say? What's confusing to a lot of people is that there seem to be infinitely many steps that you walk through to basically to get to here, you have to walk half the distance. But to walk half the distance, you have to walk the quarter of a distance. And to do that 1/8 and to do that 1/16. You understand? You had to cross infinitely many points, so to speak, or infinitely many partitions. Is that possible? Well, let's try this game and see what you say in this situation. So we have creation of the universe experiment. It's a simple experiment, but let's say that what we're going to do is we're going to populate the universe with infinitely many stars, and those stars are labeled star 1, star 2, star 3, 4 million, you understand, by integers. So we do that in two ways. So here is experiment 1. Half a minute before 12, we will make stars 1 through 10 appear in the universe, where star number 10 immediately extinguishes, immediately vanishes from the universe. So we have the situation. So you can see that the number of stars in the universe is 9 times 1, half a minute before 12. Yes? Notice the similarity, right? I'm taking half steps. Next procedure, 1/2 squared minutes before 12. I will make stars 11 through 20 appear in the universe, where star number 20 is immediately extinguished. And so you see that we gained, a net gain is 10 stars appear, 1 is extinguished, we gain extra 9 stars. So it is now 9 times 2. Clear? Next situation is we make stars numbered 21 through 30 appear, with 30 instantly vanishing. So you can see that 1/2 cubed minutes, or 1/8 minute before 12, we have 9 times 3 stars. Do you agree? Everybody is with me, guys? You pay attention? And because it's difficult to describe each step, let me describe step n. Step n is just a generic step. What happens? At step n, stars numbered 10 times n minus 9 all the way to 10 times n appear in the universe, with star 10 times n immediately vanishing. And you have 9 times n stars. Now again, guys, there is no such thing as n. What I mean is I described all the steps at the same time. So if n is equal to 1, I describe first procedure. If n is equal to 2, I describe second procedure. If n is 3, 4, 5, I describe each procedure. You understand? With one sentence, I describe each procedure, what to be done. Are you clear with that? So that's what the function of n. N is just saying, just tell me what n is, and that would be that nth procedure. If n is 10, that tells you what to do at the 10th procedure. If n is 1,000,000, it tells you what to do at the 1,000,000th procedure. Now the question I have, guys, is how many, that's first question for this experiment, how many stars are in the universe at 12? You understand my question, right? So half a minute, a quarter a minute, 1/8, how many stars do I have in the universe at 12? So Elazar says infinitely many stars. What about the rest of you? What do you think? Let's see what you say. Okay, Liam says infinitely. Also, Brianna says that. And okay, well, anybody says anything else? Okay, Elazar says you never actually get to 12. Thank you, Elazar. I was waiting for that comment, you see. Do you see that I always hear that, at least from one person, when the class is big enough, the person says, I don't get to 12. Well, if you don't get to 12, then now suddenly you understand what was in the mind of Zeno. If you say that, you say, if you don't say that, maybe you still don't understand. But when you, so what do you think, Elazar? Do you believe you get to 12 or you don't get to 12? That's the interesting question here, right? So you see, before we divided space into steps. Now we divide time into steps.
Depends how you look at it.
Mm-hmm. That's a very Jewish answer.
If you look at it as steps, then you will never get to 12. But if you just look at it, just time goes on, no matter how many stars you put in, eventually will get to 12 o'clock.
So, so do you get to 12 o'clock or do you not get to 12 o'clock?
It depends who moves the clock. If it's you who moves the clock, like every time you add another 9 stars, you move the clock, then you'll never get to 12. But if the clock anyways keeps going by its own pace, you'll...
Well, your task is to just make the stars appear in the universe and not to move the clock.
Then of course you will get at 12.
Okay, so then you believe you will get to 12, but if you move the clock, somehow you will not.
No.
That's very interesting.
Because your steps are infinite. They're never ending.
Many steps, that's true. All right, guys, any other ideas? So now I'm going to ask you the next question. I mean, a few of you, only a few of you answered, though the others are what, paralyzed? Do you think it's infinity? Do you think you don't get to 12? Or do you think there is another answer to it for experiment 1?
I think it's the same thing. Same thing. It's infinite.
So you
infinite
believe
you'll never get there.
I have infinitely many stars, yes, Elazar?
And you'll never get there. It's the same thing, because there's no such thing as infinite stars.
Maybe there is, maybe there is not.
Not in our universe.
I don't know about our universe. Mathematically, you can think about it, right? About what's a universe like? That's already another question. So guys,
basically, this person is just saying that it's almost like your distance is always being prolonged into fractions. It's like an ongoing thing, but never completing it.
so if you run this experiment, will you reach 12? If you were to start doing this experiment as inscribed, will you reach 12? Janie.
I have a different question. What happens if you don't create stars? Just let time to pass. Of course you will reach 12.
Okay, so then Elazar, you say you do reach 12, yes?
Just because you're creating stars doesn't make it time to stop.
Okay, that's a good interesting analogy, right? Because you're creating stars, it doesn't make time stop. Okay, so we will get there again, guys. I'm hoping it's interesting to you guys. You're thinking about it, right? So all of you, think infinity if you get to 12? What is your answer? I know Elazar gave me 2 interesting answers. What about the rest of you? Some of you told me infinity. Everybody says the same, infinity? Simple question. What happens after step 1? I gain 9 stars. After step 2, I gain another 9. So by step 2, I have 2 times 9. By step 3, I have 3 times 9. Do you agree?
This kind of reminds me of limits when you show the image of how things start to get like it starts to reach a point where it gets more thin, this line.
Mm-hmm. Well, the line thin, you mean short. Maybe you mean short, not thin, but short, right? Well, it's a limit, yes, it's a sort of limit that we do, but the question is what happens at 12. So that was question 1. I think some people, Erin said something interesting to say. She said the 10 stars are vanishing, okay? So you say infinitely many of them at this experiment. Now tell me what happens in experiment 2, okay? Those are both the same question. Okay, in experiment 2, you just make a slight modification, you understand? So you begin at half a minute before 12, you create stars 1 through 10 with 1 immediately extinguished. Not 10, but 1 immediately extinguished. Are you with me? So how many stars do I have at half a minute before 12? That's 9 times 1, same thing, right? 10 stars appeared, 1 star is extinguished. Next, at half squared minutes before 12, I have stars numbered 11 through 20 appearing, but this time star number 2 extinguished. You understand? So this is the situation that you're observing, 3 all the way to 20. So you lost 1 star and gained 10 stars. So a net gain of 9 stars. So it's 9 times 2. Do you agree? A 1/2 squared, you have 9 times 2 stars. Next, at step 3, that's 1/2 cubed before 12. You gain the next batch of 10 and lose star number 3. And this is describing what happens in general. Yes? That's describing what happens in general at any step. I hope you see the pattern. My question is, for the second experiment, how many stars in the universe are now? Did you understand the second procedure, guys? If you need me to repeat it, let me know. One star is removed every halving in both experiments, but here in experiment 1, first I remove the 10th star, then the 20th star, then the 30th star. In experiment 2, I remove first, then second, then third. Right? I always add the batch of 10s and I remove just different nominations of stars. And my question is there any difference between the number of stars in first experiment or second? Yes, every halving I'm adding 9 stars, correct, Grant? How many stars?
I mean, if the time gets more complex and you're increasing n, I think there's going to be a point where there's going to be n as infinity before 12.
N is just the step, so it's just 1/2, 1/4, 1/8. So 1/2 to a very large power is just a short duration before 12. Very, very little duration before 12. You just add batches of stars. Yes. So the question is, at 12, how many stars do we have? Strangely, you're all silent, guys. Okay.
Is this a probability question?
It's not. Why is it probability? Whereas it's not a probability question. It's the answer is why is it probability? The answer is not nothing to do with probability here. Okay, so Jeffrey says infinity. Do you understand what's happening, guys? What are you lost, Moshe? Not really. What bothers you guys? You just imagine. I mean, it's not like you say, what do you think? Mathematics, you say right answer, wrong answer. That's a wrong view of the subject. You're just thinking and trying your best to see what's the situation, right? There's not like, I'm not on any authority on anything, right? And nobody should be authority for you. You just think about it and ask yourself what's reasonable about it. So in the first experiment, everybody understands what's happening? As I carry more steps. Sorry, Jenny, what do you want to say?
Yeah, could you just one more time review the experiment?
Yes, both experiments, guys. So what happens, what you do is you have the time, 1/2 minute before 12, then 1/4, then 1/2 cubed, 1/2 to the 4th power. You understand, right? You make very small fractions of time. And the question is then at each fraction of time, in the first experiment, you add a batch of 10. So after first procedure, you take 1 through 10 and remove the 10th. Then you throw in 11 through 20 and remove the 20th. And then you throw 21 through 30 and remove the 30th. That's the procedures. You understand what happens in experiment 1? So what happens with each step? With each step, I gain extra 9 stars. Do you agree?
Yes.
Right? So how many steps will I execute? You can clearly see infinitely many steps to 12, because 1/2 squared, 1/2 cubed, I have 1/2 to any power. So there are infinitely many steps, and each step gives me extra 9 stars. My question was, in experiment 1, how many stars are 12 exactly? Right? So Grant, what do you mean by 9 times n? That's just what is n? So infinite stars, some people say in experiment 1. Now what about experiment 2? Very similar procedure.
I don't think it's, I think it's undefined.
Okay. So then in the second procedure, 1 through 10, but 1 disappears. So we have 9 stars gained. Next procedure, 10, or 11 through 20, but 2 disappears. You understand? And then 21 through 30 and 3 disappears. Then 31 through 40 and 4 disappears. Do you understand what's happening in the second procedure? Now my question is, in many of you, at least some of you, I'm not sure many, said that in the first experiment the answer is infinity. And in the second procedure, what do you say? Is it the same answer, or is there any difference? And it's interesting that I asked this question, you're all hiding suddenly. Guys, turn on your cameras, I want to see your faces. I want to see what happens there.
What if the first one is positive infinity and the second one is negative infinity?
Well, why not? I mean, I'm just asking you what it is. Or it's not defined, that's fine. Just what do you think about it, guys? Do you see anything there? Yeah, well, in any case, you're losing infinitely many stars, right? Because there are infinitely many steps, you're losing infinitely many stars. But how much do you have at 12? How many remain bright at 12? That's my question. For experiment 1 and experiment 2, is it the same answer or different answer? And what is it for each? How do you answer such questions, guys? Okay, so I mean, you are kind of puzzled. I'm not sure. It's you look like deer in, you know, on the highway, right? You do make me want to run you over. Yes, that's good if you're puzzled. Now, what's the puzzle? You see what you do in mathematics? That's why I mean, it's an art of thinking. Grant always likes to ask me, what's the purpose of what's an application? What's the use of something? And I think if you do mathematics, it might make you a more interesting person. It might give you interesting thoughts and interesting ideas, right? And that's pretty much why you study mathematics. It's not because you say 2 + 2 or something like this, right? It's we need to know how to do mathematics. We need to learn that through mathematics, not what you did in high school. So here is, let me then explain to you how I would have thought of this question, right? So first of all, Elazar raised a very good point. Do you ever reach 12? Okay, let's for a moment ignore that question for a moment, right? And then we'll address it. Suppose I do reach 12. And then whatever complexity happened, let me try to be simple. If this is my universe, I can be a little bit like a monkey. I can just push my hand into the universe and ask myself, do I pull something out of it? Now, can I pull a star out of the universe? In the first experiment, can I pull out star number 1? Well, yes, it appeared in the first experiment. It appeared after first procedure and stayed there. Yes? Can I pull star number 2? Yes, it appeared in the first procedure and stayed there. Which star I cannot pull out? Star number 10. It disappeared on the first procedure. Star number 20 cannot be pulled out because it disappeared on the second procedure. You agree? And in fact, if you think about it, every star whose number is divisible by 10 cannot be pulled out because it disappeared. But there are other stars remained. The limit is infinity. Do you agree? Because we're gaining with each step 9 stars. So the limit is infinity in experiment 1. Now let's think about experiment 2. Can I pull star number 1? Can I pull star number 2? No, because it disappeared after second procedure. So star number 2 is not there. Can I pull star number 3? 4? The 4th star disappeared on the 4th procedure. Do you see what I'm saying, guys? Which means what? Which means that the universe is empty, completely dark. The stars in both situations, you know, the heavens were becoming brighter and brighter and brighter, but in one situation at 12, complete darkness. In the other situation, it remains bright. Do you understand? And it's getting brighter and brighter, faster and faster in both situations. Are you following me, guys? Isn't it? You see what I'm saying? So that's a distinction. Limits are very different from the limit in both cases is infinity. Do you see that? The limit is as you approach 12, you're gaining stars. The limit is infinity. But in one case, if you do reach 12, the answer is 0. And in the other case, it's infinity. Do you understand that? Now, then Elazar said pretty much what I think about time. So in experiment 2, you cannot pull 1, right? Star number 1 disappeared, star number 2 disappeared, and all the remaining ones disappeared, okay? And of course, when you speak about time, intuitively, guys, you should have an intuition about time. Intuitively, time does not care what you do, right? And I right away think of this very nice poem, right? And it says, «А время торопит возница беспечный, и просятся кони в полет». It's by Akujava, and rough translation of it, and time is rushed by an indifferent driver, and horses ask to move forward. You understand that time, it's like this coach that completely doesn't care what you do with it. You can be fast or slow, but time will just flow on. And that's the naive intuition about time. Good? But I will show you the paradox is not over. First of all, if you think about the theory of relativity, you see that there is a limit, a speed limit of how fast you move. And let me tell you at least an interesting conclusion, guys. So to understand it, it's another thing. But let's just ask, do you know what is a light year, guys? So stars are very far away. Even light that travels very rapidly, it takes a long time to reach from one star to another, right? So let's say a star that is from here, 100 light years away. If I send a spaceship that travels at the speed of light, how long will it take it to reach its destination? What do you think? A spaceship that, so I'm traveling to a star that's 100 light years away. I'm sending a spaceship that travels at the speed of light. How long will it take it to reach? So Brian says 100 years. Well, and if you are the passenger, guys, okay, if you're a passenger of that spaceship, how long will it take you to reach the star? What do you think? Well, no, Elazar, you're thinking about the sun, and I'm saying, let's say we have a very far away star, 100 light years away, good, and a space shuttle is traveling at the speed of light. If you're a passenger of that space shuttle, how long will it take you to reach it? So you say 100 years. Actually, no time whatsoever. If you are traveling at the speed of light, the traveler, the time completely stops. You would reach it in no time. For a person observing the light beam traveling, that will take 100 years to notice the light beam. Well, the light beam will take 100 years to arrive. You understand? It would look like it took 100 years, but for the traveler, time will be completely stopped. So time might care about what you do. That's one aspect, okay? And that another aspect I want to tell you guys is something that we will deal with in the next lecture. It has to do with my nightmares. Why every time I go to sleep, every time, it never happens, I have very, very deep dreams about something very frightening. And I will share with you what I dream about, at least partially. Okay, so let's stop the recording. We will do that next lecture. I hope you were able to enjoy a little bit here. We will do a little bit of questions. We will solve some questions and, limit questions. And then we can discuss, if you are confused about long division and things like that, we can try to discuss it here. Good. I'm stopping the recording.
Thank you, Professor.
Good.